Now we are going to the next problem, example number 3. The rotor shaft on a helicopter drives the rotor blade that provides the lifting thrust force to support the helicopter in the air. As a consequence, the shaft is subjected to a combination of torsion and axial loading for a 50 mm diameter shaft, transmitting a torque T equal to 2.4 kN and thrust force P 125 kN. Determine the maximum tensile stress, maximum compressive stress and maximum shear stress, analytical and graphical method. So with this problem, you can understand we required all the concept of the solid mechanics or strength of material to solve this problem. So basically, if you see this diagram, there is some thrust load applied to lift the helicopter and some torque is also applied here to twist the blade. So if you draw that ABD of this shaft, then some tensile type of loading is applied outward from the body and some twisting moment is applied. Due to this combination type of loading, what are the different type of the stresses produced in this element, that we have to find out. And we have to also find out the combination of different type of the loading, that is in the concept of maximum principal stress theory and maximum shear stress theory, analytically and using the Mohr circle. So can you please first tell me which type of problem it is? I think due to this tensile force, there are some tensile stresses is produced, which is normal type of stresses, and due to this torque, there is some torsional shear stresses produced. So it will be the shear type of the stresses. So basically it will be combinations of the normal and torsional shear type of the problem. Okay, now we try to find out the individual stresses. First we try to find out the tensile stresses. That will be force divided by the area. Thrust force is 125 into 10 raised to 3. Area diameter is mentioned 50 mm, so it will be pi by 4 into 50 square. So it will be 63.66 megapascal tensile, hence it will be the positive. The next stresses is the torsional shear stresses. Formula is the T into R divided by the polar moment of inertia J. T is mentioned 2.4 kilonewton meter. So we need to convert 2.4 kilonewton meter to Newton mm. So first kilonewton to Newton multiplied by 10 raised to 3 and again meter to mm multiplied by another 10 raised to 3. So it will be 2.4 into 10 raised to 6 into R, as the diameter is 50, so R is 25. Polar moment of inertia of the solid shaft is pi by 32 into 50 raised to 4. So the answer is coming 97.78 megapascal. Now we have to draw this stresses in the element diagram. So I just show all the stresses in this element diagram. I just explain this, how the stresses is shown in this element diagram. I write down that same number here in that element. So this is the 1 number point, this is 2 number point, this is 3 number point, and this one is the 4 number point. So as the tensile stresses applied in outward directions on this, so here this is the direction of the tensile stresses. I have shown it here. Along the y-axis it will be 63.66. Similarly here also along the y-axis 63.66 in the outward from the element. Now the most important thing is the direction of shear stress. To find out the direction of the shear stress at 1-2 plane, so you can see it here, the torque is applied in this direction. So in this 1-2 plane, the shear stress is produced. The shear stress is produced in this direction, from right to left or from 2 to 1. So in this diagram we are again showing the shear stress produced on this plane, 1, 2 plane, is from right to the left or from 2 to 1 direction. Now once I have the direction of shear stress in one plane, on the opposite plane it will be exactly opposite to that top one. As in this plane it will be rotating in anti-clockwise directions. Hence on the other xy plane it should be rotating in the clockwise direction. So tau xy directions is the clockwise directions only. According to the sign conventions, what we had explained in the part 1, please refer my part 1 sections for the directions of the shear stresses and the normal stress. We know that in xy plane, that is in the vertical plane, if shear stress is applied on a clockwise directions, that will be considered as a negative value. So as it is in clockwise, we are considering it will be minus 97.78 at xy plane, but at yx plane it will be positive 97.78 megapascal. Shear stress basically the torsional shear stress, and whatever the tensile stress we are applied, that is along a y-axis, that's why it is called the sigma y. Okay. Now, due to the different type of loading applied in this 1, 2, 3, 4 element, now we need to find out the maximum tensile stresses, maximum compressive stresses using the principal stress theory, and maximum shear stress theory. We have to find out the maximum shear stress also, analytically and graphically. So first we check the analytical formula. Maximum and minimum principal stress formula is this: sigma 1 and sigma 2 is equal to x plus sigma y by 2 plus minus under root of sigma x minus sigma y by 2 whole square plus tau xy square. With the proper sign conventions, we need to put all the value here. So first, sigma x is 0, sigma y is plus 63.66, tau xy is basically is a negative 97.78, and the final value, when you consider positive, then the answer is coming 135 megapascal, that is positive value means tensions. When you consider the negative value here, it will come in negative 71 megapascal. That means it will be the compressive type of the loading. So that's why they ask you the maximum tensile stress, answer is 135 megapascal. Maximum compressive stress, the answer is 71 megapascal. Now we also need to find out the maximum shear stress using the analytical formula first. So the formula is tau max plus minus of mod of sigma 1 minus sigma 2 divided by 2. Now again check the sign convention. Sigma 1 is positive 135. Sigma 2 is basically negative 71. So it will be negative of negative 71. So it is coming, basically it will come in the positive finally, divided by 2. So the answer is coming plus minus 103 megapascal. Using the analytical formula, we are finding out maximum tensile, maximum compressive, or we can say the maximum principal stress, minimum principal stress, and maximum shear stress. Now, the same problem we also need to find out using the Mohr circle. So just check it here. Graphical solutions. First, we need to find out the x coordinate and y coordinate of the point x and y. I am suggesting you, please refer my online video uploaded earlier on a Mohr circle. It's a very good explanations I have given it. So please refer it, and also request you for this type of that video in continuations, please subscribe my channel and click on the bell icon to notified whenever I am uploading a new video. So here for the graphical solutions, x coordinate sigma x and tau xy is 0 and minus 97.98. Y coordinate sigma y and tau yx is a plus 63.66 and 97.98. Scale I am taking that 1 mm is equal to 1 megapascal. Means everything to be divided by that 1 megapascal and it will be converted into that mm directly. So step by step I explain you how to solve it in the Mohr circle. First is the axis. One thing to be remembered in this particular axis, notations of that axis is the positive sigma along x-axis, it is towards the right one. Negative sigma along towards the left, along the x-axis only. But the only exceptional case is the tau. So tau along y upward to be considered as a negative tau and downward to be considered as a positive tau. So that is the only thing you remember. I am using that Igor and Popov and that Andrew Patel's or Johnson book. Every book is given the same type of that sign convention. So after plotting that sigma and tau axis, we need to plot the x and y coordinate. First, I just want to plot that y coordinate. So what is that y? Sigma y is 63.66. Similarly, tau xy is coming positive 97.98. I have to just put that y point first. So it will be plus 63.66. So I have to mark it along that sigma axis, and plus 97.98, which is the downward directions along the tau axis. So we get the point y. Similarly, I want to plot that x coordinate. Just check that tau is 97.98, but it will be the negative value. That's why it will be on the upper side on the tau coordinate. And sigma x is coming 0. So it is along the y axis only. So here I am getting that x coordinate. Sigma x and tau xy is equal to 0 plus 97.98. After getting y, x and y, the next step is we have to just join it. Wherever this joining line intersect that sigma axis is my center point of the Mohr circle. Take that point as in center, and radius is equal to the half of the distance xy. Draw a circle. Wherever this circle cuts the x-axis or the sigma axis, that will be our maximum and minimum principal point. Distance which is in bigger from that origin point is the sigma 1. It will be in the positive direction, that it will be right side of that y-axis. So hence it will be plus 135 megapascal. Then minimum one is on the left hand side of the y-axis. That's why it's coming negative 71 megapascal. So you need to measure that distance basically 135 mm and multiplied by that 1 megapascal, as my scale is 1 mm is equal to 1 megapascal. So we got that maximum tensile stress 135, maximum compressive stress 71 megapascal, and the maximum shear stress, you just draw a vertical line where it cuts the circle, measure that distance. So that will be tau max plus minus 103 megapascal. So that's the way to solve the same problem using the Mohr circle also. Thank you very much. I think with this two problem we have understood, or in the last three problem we have to understood. The first one is the normal type for a vertical pole. The second one is the tensile and the bending type, again normal. Third one, we had solved it, the torsional shear stress and that tensile type, so normal and shear stress. Now for remaining part, I just want to cover the other type of problem. So please subscribe my channel, press on the bell icon for the notifications. And if you have any doubts or any comment, please write down on the comment box on my YouTube channel, so we can improve upon the content of the delivery of this problem. Thank you.